Today I'm very pleased to be sharing our recent work on surpassing the loss-noise robustness trade-off in QKD. You can find the work at the following link. And before we start, I also need to say a big thank you to my collaborators on this project, Emilian Levy, who was previously a postdoc at Bristol, Theo Stromberg, who's based in Vienna, and Matt Stafford and Julia Rubino, who are also based in Bristol. So I'd like to start this talk by telling you where we're going. So in this talk, I'm going to present a discrete variable QKD protocol that utilizes continuous degrees of freedom and antisymmetry to achieve an increased robustness to loss and noise compared to existing schemes. So this might sound like a bit of jargon right now, but hopefully as we go through the talk, what I mean by this will become more clear. And this is essentially just the message I want you to keep in your mind as we go through. So now we know where we're going. How are we going to get there? Well, I'll start by telling you what I mean by this loss-noise robustness trade-off. I'll then present our solution to it in the form of a logical qubit encoding. I'll then analyze its robustness to loss and noise through the form of a security analysis. And finally, I'll give a summary and an outlook. So what is the loss-noise robustness trade-off? Well, I don't think I need to tell anyone here what QKD is or why we care about it for all of its many industrial applications. But what I maybe can clarify is that whilst in principle, QKD looks quite simple, in prepare and measure, Alice prepares one of a set of non-orthogonal states and sends it down the channel to Bob, who makes measurements in those bases. Real implementations are far from simple because there's going to be noise and loss throughout the channel. Now, I'm sure we're all aware of the challenges that loss imposes on QKD protocols because it limits the distance over which the key can be shared. And of course, in the last decade or so, we've seen many seminal works along this line. The plot bound demonstrated a fundamental limit on the rate loss scaling. Subsequently, twin-field QKD demonstrated how this limit could be overcome by using an alternative user configuration, and is now known to have one of the best scalings of any QKD protocol, and seen many successful demonstrations, as we've heard throughout this conference. Noise, on the other hand, transforms the states between Alice and Bob. So for example, the state of a polarization encoded qubit will rotate as it travels down an optical fiber due to the birefringence in that fiber. These transformations give rise to errors, which, because Alice and Bob don't know if there's an eavesdropper present, have to be attributed to an eavesdropper. These errors therefore lower the rate at which the key can be shared, and in the worst case, which is actually the most experimentally expected case, we actually get no key rate altogether. That is at least unless we employ noise compensation techniques. So I just want to take a moment to really highlight what goes into these compensation techniques. We've heard about a lot of different examples through this conference, but let's just take a specific example here. So let's look at it through the lens of twin-field QKD. So we've established that this is a very successful protocol in terms of experimental demonstrations. And in principle, it looks quite simple. We have, there we go, Alice and Bob preparing two identical laser fields and then sending them down to channels and interfering them on a central beam splitter. But in a real implementation, there's going to be fluctuations across these channels. So the phase, the frequency, the polarization, etc., may fluctuate as they travel down these channels. So this means that a real implementation becomes a lot more complicated. We need multiple active feedback and stabilization mechanisms in order to accurately compensate the phase and the polarization of the two laser fields. And we also need some way to disseminate identical frequencies, for example, with hundreds of kilometers long Mach-Zehnder interferometer structure, although we also heard of many other ways to do this in yesterday's tutorial. So this means that whilst these experiments are certainly very impressive, they come with extensive overheads and limited industrial scalability. And in fact, a recent paper on studying polarization compensation techniques for QKD networks highlighted how procedures that may be easy to implement in simple two-user quantum links may not necessarily be scalable as we start building large-scale and heavily interconnected quantum networks. So highlighting the fact that whilst we need compensation techniques for the effective operation of QKD protocols, they come with their challenges in terms of industrial scalability. So this led us to ask the question, is there an alternative solution? Is there an alternative way for us to perform QKD that doesn't rely on these extensive compensation techniques? And it's probably unsurprising that the answer lies in principles from error correction. Essentially, we can encode our states into logical qubits that have an inherent resilience to noise. So by taking some larger dimensional Hilbert space, we can find some subspace of that that has an increased resilience to noise. So let me give you a specific example of this. Let's consider that we have a channel that applies the same unitary to every qubit in an n-qubit state, but it's going to be, the parameters of the unitary will be unknown and fluctuate randomly with time so that we can model some sort of noise. Now, of course, if we send just one photon down the channel, we don't know what the parameters of the unitary are, and we're going to have to estimate the noise in the channel and perform some compensation. But already when we go to 2 qubits, it turns out that there is a state, the antisymmetric Bell state psi minus, which is perfectly invariant under this noise. So this means if we send the state psi minus down the channel, no matter the parameters of the unitary, the same state psi minus will come out. So existing schemes have used exactly this idea to propose noise-resilient variants of QKD protocols. There was a 2-photon scheme which proposed a noise-resilient protocol that increased the robustness to noise compared to BB84, but was not perfectly noise-canceling. On the other hand, by using 3 or 4 photons, we could get perfect resilience to noise and all the requirements we need for security, but at the cost of having 3 or 4 photons, which makes them highly sensitive to loss. Because if even 1 photon is lost in the logical state, then the whole physical logical qubit is compromised. So with this, we see that there's a trade-off between the loss robustness of our protocols and the noise robustness. On one hand, protocols that scale well with loss, such as twin-field QKD and BB84, require these extensive compensation techniques for their effective operation. On the other hand, we can increase the number of qubits in the logical state to get perfect noise cancellation, but at the cost of having exponentially worse scaling with loss. This is where our work comes in. So in this work, we present a new scheme that minimizes the number of photons needed while still avoiding the need for compensation techniques. So it might sound like we're playing a bit of a trick right now. So what exactly are we doing? Well, essentially, we're going to exploit the properties of the photons in which we're encoding our information. So we're going to encode our information into continuous photonic degrees of freedom. So let me show this a bit more visually. In existing schemes, we have 2 variants. We have our discrete variable QKD protocols, where if we want to get some sort of noise resilience, we take many physical qubits and tensor product their Hilbert spaces together to get some larger dimensional space. We're not doing this. On the other hand, we have continuous variable schemes where we can get an infinite dimensional space essentially for free by encoding our information into the infinite number of excitations of a single mode of the electromagnetic field. So this is our continuous variable picture. We're also not doing this. We're kind of doing the opposite of this. So instead, we're going to take a fixed finite number of excitations, but now we'll superpose them across an infinite number of modes. So just to draw the distinction again, in continuous variables, we have an infinite number of excitations in a finite number of modes. Here, we have a finite number of excitations across an infinite number of modes. And so to draw that distinction, we'll call this a continuous degree of freedom encoding. Okay, So what have we seen so far? We've seen that practical implementations of QKD are limited by noise and loss. We've seen that noise can be mitigated by increasing the dimension of the encoding space, but this comes with a trade-off in the loss resilience. And now we've seen that by using the continuous domain, we might be able to do this without increasing the number of photons. So with that, what is our encoding? Well, our protocol is going to follow the standard BB84 scheme, but now we'll use logical qubits rather than physical qubits, which means we need to make one small adjustment, which is to say that now, because Bob might measure his state as lying outside the logical subspace, he'll discard his outcome if this is the case. So what exactly are these logical states? Well, we're going to build up our states in two steps. In the first step, we'll define single photon states. And in the second step, we'll take these states defined in the first step to define two photon states to form a logical encoding. So in the first step, we'll define single photon frequency bin and time bin qubits. So by frequency bin qubit, I mean that if we have some spectral amplitude peaked around a frequency omega naught, we'll say it's in the state 0f. If instead it's peaked around some frequency, say omega 1, we'll say it's in the state 1f. Similarly for time bin qubits, if the temporal amplitude is peaked around some early time tau naught, then it's in state 0t, and if instead it's peaked at some later time tau 1, it's in state 1t. Now in general, we can take these to be arbitrary sharply peaked amplitude functions, but for the rest of the results you'll see in this talk, we've modeled them as Gaussians. So now we have our single photon states. We need to define two photon states. So we're going to define two photon states, the first being an antisymmetric Bell state defined using frequency bin qubits. So this says if the first photon is in a frequency omega naught, then the second will be in a frequency omega 1. Vice versa, if the first is in omega 1, the second will be in omega naught. And then we'll define a second state, which now will be the antisymmetric Bell state defined using time bin qubits. So early late minus late early. Now what's interesting about these two states is it turns out we can actually tune the parameters of these encodings, omega naught, omega 1, tau naught, tau 1, such that these two states can be made perfectly orthogonal to each other. And I apologize for those who can't read that at the bottom. But it's just what I just said. So what this tells us is that actually we can define a logical encoding where our logical 0 states are our antisymmetric Bell states defined using frequency bin qubits, and our logical 1 states are antisymmetric Bell states defined using time bin qubits. So now we have a logical encoding. The next step is to analyze its robustness. But before we do that, I just want to take a brief aside to consider the experimental feasibility of this scheme. The reason being is that whilst this work is purely theoretical, it's been motivated by real-world challenges, and so it was important to us that we consider whether it has experimental implementability. And I'm also sure that experimentalists are probably going to be wondering this because we've got some quite exotic states. We've got, to produce and measure antisymmetric Bell states in time bins and frequency bins and their superpositions. So in the next two slides, I'll just present two simple proof of principle ideas for how this scheme could be approached. So from the state generation side, these states could be generated using domain-engineered nonlinear crystals. So these are crystals which produce entangled pairs of photons by, for example, spontaneous parametric down conversion, and by tuning how you pole the periods of your crystals, you can produce essentially arbitrary phase matching functions, and by also tuning the pump spectrum, you can therefore produce almost arbitrary two-photon states. So in this way, we can produce a crystal that creates our antisymmetric frequency bin state and one that produces our antisymmetric time bin state. And to produce superpositions, we could put two of these crystals in series with some appropriate phase matching conditions. And some simple simulations that we performed show that we could produce these states on the orders of hundreds of megahertz, so certainly competitive with current experimental protocols. The state measurement procedure, on the other hand, is a bit more involved, and just to highlight here that this is a deliberately minimal and non-optimal example, just to show that there is, in principle, an experimental path to performing this measurement, but an optimized scheme for this would merit its own dedicated study. But essentially, the measurement works kind of like the reverse of doing the state generation. So essentially, Bob can interfere the incoming state from Alice with a state that he produces by one of the same crystals. So to say that more clearly, if Bob takes the incoming state from Alice and, say, destructively interferes it with a crystal generating the antisymmetric frequency bin state, if Alice's state was also the antisymmetric frequency bin state, the states would cancel and there'd be no click on the detector. If instead she sent the time bin state, then they wouldn't cancel out and there would be a click on the detector and Bob could deduce that Alice sent the time bin state. So we've now seen that approaches for how we could perform the state generation and measurement. And so we see that our scheme is not just a theoretical ideal, but has some near-term feasibility for an implementation. So with that, let's just go back to where we were. So as a reminder, we said that our logical zero states are our antisymmetric time Bell states defined using frequency bins, and our logical one states are our antisymmetric Bell states defined using time bins. So now I've sort of claimed that we want to have some sort of resilience to noise and loss, but I haven't necessarily shown that that's the case. So in the second half of this talk, I'm going to demonstrate the robustness of our scheme by performing a security analysis. So to state this more clearly, the goal of the second half of this talk is to find the impact of noise and loss on the key rate of our protocol. Now, we perform our key rate analysis using an open source package developed by Norbert Lutkenhaus's group at the University of Waterloo. I think Devavish also mentioned it yesterday in his tutorial. And using this, we can find numerically evaluate key rates to find an asymptotic lower bound for our protocol. And this key rate solver needs three things to go into it. So the first is a mathematical description of Alice's prepared states. Now, we know that these are the logical 0 and the logical 1 states, but we also know that these states are themselves two photon states, which are comprised of four non-mutually orthogonal states, the frequency bin and time bin qubits states. Now, since in principle, Eve could find some sort of strategy that exploits the two-photon structure of this scheme, to be fully rigorous, we want to account for this two-photon structure. And so to do that, we just need to rewrite these four states into an orthonormal QQuart basis, which we can do using a procedure like Gram-Schmidt orthogonalization. In this way, we now have a mathematical description of Alice's prepared states in the form of a 2 QQuart basis. The next thing we need is a mathematical description of Bob's measurement projectors. Well, we can use exactly the same formalism that we've just identified and write them as part of a 2 QQuart basis. So we have this. Now the final thing we need is a mathematical description of the channel noise model. And this bit is a bit more complicated. The reason being is that we have these continuously encoded discrete variable states. And so on one hand, we want a noise model that allows us to compare our scheme with existing schemes. So we do this formally through a model which we call the frequency beam splitter model. On the other hand, this is not necessarily the most expected type of noise. So for that reason, we also can analyze our protocol under the chromatic dispersion model, which is a more experimentally expected type of noise. So in the rest of this talk, I'll first present the results under the frequency beam splitter model, so that we can draw some comparisons between our scheme and existing schemes. And then at the end, I'll just present the results of the chromatic dispersion channel. Okay, so what is a frequency beam splitter? Well, I've said that we want to be able to compare our scheme with existing schemes. And existing schemes, the discrete variable protocols, assume that we apply a unitary to the multiple identical physical qubits in our logical states. In contrast, our protocol is continuously encoded, and we have two fundamentally distinct types of qubit states. The first is our time-bin qubit states, which we can Fourier transform to represent in the frequency space, where they become very broad. And the second is our frequency bin qubit states. So these are much more sharply peaked. So we see we have these two fundamentally distinct types of qubits. So now if we want to apply a unitary to our physical qubit states, we essentially have to pick one. So we're going to pick the frequency bin qubits. In this way, if existing schemes are also encoded in frequency bin qubits, we can draw some sort of comparison between our scheme and existing schemes. But how do we apply a unitary to frequency bin qubits? Well, let's consider that we have a beam splitter that acts on the frequency modes omega 1 and omega 2. I've drawn it here in the spatial modes just to make it a bit more visual, but essentially the frequency beam splitter will just act on these frequency modes so that the state's input will be output into a superposition of belonging in these two modes, omega 1 and omega 2. So we can now write this as a matrix, where the matrix is parameterized by some angles theta and phi, which represent rotation angles on the single frequency block sphere. And now we've just relabeled these to acting on modes omega and omega plus mu. But here we're assuming that this acts on infinitely narrow single frequency modes of the field. In reality, the frequency bin states are never going to be infinitely narrow, and so we need to generalize this slightly. So to do that, we'll now say that the unitary operation acts across a continuous spectrum of frequencies in a range epsilon around the frequency omega. This means then, if we apply this generalized operation, this frequency bin state peaked around a frequency omega will be transformed to being around a state omega plus mu. Vice versa, if it was around state omega, it will now go to being around state, omega plus mu, it will now go to being around state omega. So this then is applying a unitary to our frequency bin qubit states. But as a sneak peek, it's not going to have the same effect on our time bin states. Okay, so now we have a description of, a mathematical description of our channel noise on the continuous variables, continuous degree of freedom states. We need to find a way to write them that we can use for our numerical solver. So formally, we can do that by basically finding how our input states, single photon input states, transform into these transform states. And in this way, we have a full 2-photon treatment. But it actually turns out it's enough just to consider the effect of the noise at the logical level of our encoding. In this way, we can also gain a bit more intuition about the results of our scheme, and we actually recover results almost identical to those when we take into account the full 2-photon structure. Okay, so what effect does this noise have on the logical level of our encoding? Well, our frequency bin states, so our logical zero states, are going to be unaffected by the noise. The reason being is that we said that they are encoded in these antisymmetric frequency bin states, and we're applying a unitary on frequency bins, and we saw earlier that the antisymmetric Bell state is invariant under such operations. The time bin states, the logical 1 states, in contrast, will be affected. So how are they affected? Well, to find out the effect of the channel on the logical states, the antisymmetric time bin states, so if we say that the noise transforms the time-bin state into some transformed state, psi prime minus time, then we need to know three things in order to find the effect that it would have on the security of our protocol. The first will be the probability that Bob measures the correct state, so the probability that Bob measures the untransformed state given that the transformed state arrived. The second is the probability that Bob measures the wrong state, so the probability that Bob measures the frequency bin state given the transformed time bin state arrived. And finally, the accumulated relative phase, so the phase that the transformed state accumulates relative to the time bin and frequency untransformed states. And this is going to give rise to a phase error, so our error in the logical X basis. So when we go and calculate all these things, we find that we get a negligible bit error rate, we get a small accumulated phase, and then we get a reduction in fidelity. So we see that as the rotation angle theta increases, the fidelity of the states of the transformed time bin state reduces. But we also see that as the width of this noise parameter epsilon increases relative to the width of the transformed state in the time domain, we also get a more pronounced effect, which kind of makes sense because as the noise bins get wider, they're going to deform the time bin states more. But this also tells us that we can actually optimize the parameters of our encoding for the noise we expect to see in this channel. But overall, what this tells us, these three facts tell us, is that the effect of the channel at our logical level is to apply an asymmetric loss and decoherence channel. So we're now fully equipped to look at the key rate of our protocol, which, as a reminder, we use the full two-photon treatment. But we can see that it very closely resembles the fidelity curves that we saw just looking at the logical level. So we see that we get this sort of reduction in fidelity as the rotation angle theta increases. But we also see that we can, again, optimize the parameters of our encoding. So for example, here our sigma t, to increase the resilience to noise and push up our key rates. So this is looking promising. But we also said that we want to define this model so we can compare our scheme with existing schemes. So let's see how they compare. Well, the existing schemes, we had the standard BB84 protocol, which is shown in this light orange curve here. We had this two-photon error resilient but not perfectly cancelling state shown in this dark orange curve here. And we can indeed see that it's pushed up the resilience compared to BB84. And then finally, we had the perfectly cancelling three-photon state, which we can see does have perfect noise cancellation because it's independent of theta. But as a reminder, because it has three photons, it's going to have exponentially worse scaling with loss. And so for that reason, we'll see in the next few slides about how the loss compares. But because this has a worse scaling with loss, let's just compare our scheme with existing schemes that also use only one or two photons, and therefore will show a better comparison in terms of loss scaling. So these then would be the BB84 and Wang protocols. Well, when we compare to these, we see that the existing schemes show these oscillations in the key rate with theta. And actually what this tells us is that if the parameter theta is fluctuating randomly in time, which is what we'd expect in an experiment, then we actually get no key rate out of the channel. The reason being is that these oscillations are actually going between Alice and Bob's bit values being correlated here to being anti-correlated here, but corrected in a post-processing step of the key rate solver, and then back to correlated. But what these oscillations therefore tell us is that the existing schemes require stabilization mechanisms in order to get a key rate out of the channel. In contrast, we don't see these oscillations, and so we don't rely on these compensation techniques. So now we've looked at the noise, we need to compare with the loss. We need to look at the other side of the coin and look at the loss robustness of the states. So To do this, let's just start by looking at the sort of standard protocols, so BB84 and twin-field QKD, which we said have the better key rate scalings, but we've also said that they require these compensation techniques. It turns out when we actually take into account the compensation techniques required, the key rate is significantly reduced because a large fraction of the pulses sent are used to estimate the noise in the channel, and we have some sort of duty cycle to employ the correction to the effects of the noise in the channel. So now when we compare the key rates with loss, we do indeed see that we get an exponentially worse scaling with loss. So this is basically how steep our line is here. As a reminder, this is a log scale. But we also see, because we don't rely on these extensive compensation techniques, at the very least in the short to medium sort of metropolitan distances, we can get a large increase in the key rate because we're not using these compensation techniques. And so we have seen that we do have this trade-off between the loss robustness of QKD protocols and their noise robustness. And we've seen how by using these continuous degrees of freedom and antisymmetric Bell states, we can minimize the number of photons we need to perform QKD while still avoiding the need for compensation techniques. So now, just before I finish up the talk, I want to present the results for the chromatic dispersion channel, which I said is a more experimentally expected type of noise. So chromatic dispersion is when we have a frequency-dependent wave vector in an optical media, so for example, an optical fiber. Now, what this does as a mathematical description is it takes some amplitude function g of omega in the frequency domain, and it will transform it by picking up some frequency-dependent phase, where the phase depends on n, the order of dispersion, and alpha n, the nth order dispersion coefficient. So it turns out that in experimental situations, we typically only need to consider n equals 1 and n equals 2 noise. So what effect does this have? Well, for n equals 1, this just corresponds to a temporal delay of the pulses. For n equals 2, or group velocity dispersion, this corresponds to a broadening of our pulses. So we can again consider what effect this has at the logical level of our encoding. And when we do that, we again find that we get a negligible bit error rate. We find that we get a reduction in our overlap fidelity again, which we can understand by kind of looking at this sort of picture here. This will correspond to decays in our key rate. But then we also find that we accumulate an alpha n dependent phase, and this is going to correspond to oscillations in our key rate. So I'll first just show n equals 1 key rate, where we see, again, these oscillations and this decay. But it looks very similar to n equals 2, so let's move straight on to that, where we again see oscillations and decay. Well, I said before that oscillations weren't good because we're going between correlated and anti-correlated. However, our scheme still has the sort of superpower that we can optimize the parameters of our encoding for the expected noise fluctuations. So we can see here that by tuning the parameters, say our omega-1 parameter, we can change the rate at which these oscillations occur. And by tuning, for example, sigma t, we can push up the rate at which the decay occurs, and so push up our key rate. But let's just go a step further and consider what happens if we have realistic noise parameters. So let's consider 200 kilometers of silicon fiber at 1530 nanometers. The primary contribution to fluctuations of chromatic dispersion is temperature fluctuations. So taking real experimental parameters, we see that going all the way from minus 20 degrees C to plus 60 degrees C, we get the dispersion parameter changing by about 50 picosecond squared. So if we plot these onto our key rate graph, one which is actually less optimized than, say, the one on the right, which is now covered, we see that these lie well within one oscillation of our key rate. So this means that we still achieve high key rates even under fluctuating dispersion parameters. And we also see that these lie well within one oscillation peaks, which means we can have a large tolerance to how well we've characterized the dispersion parameter of our channel. And additionally, we know that we can also still optimize parameters of our encoding to push up the key rate further. And so now with that, I'd just like to summarize and say that I've presented to you our new discrete variable QKD protocol that utilizes continuous degrees of freedom and antisymmetry to achieve an increased robustness to loss and noise compared to existing schemes. In the future, we'd like to look at how we could optimize these encodings for sort of general arbitrary noise channels, whether we can extend these ideas to device-independent QKD, for example, or other protocols, and whether they can be used in other areas of quantum technologies, such as fault-tolerant quantum computing. And so with that, I will thank you for your attention and open the floor for questions.
Okay, thanks for the interesting talk. Questions welcome.
Thanks for the really, really great talk. I just wanted to ask, in terms of the encoded state, do I have it correct? You want essentially a superposition of the psi f minus and the psi t minus, as opposed to a tensor product of those two states?
So are you asking if I wanted to have the plus and minus states of these?
No. So
right.
They're both singlet states, but I think when you wrote down the logical state that you're encoding, it was the sum of those two kets.
Okay, hang on, let me just go back. Oh. Hang on, sorry, I'm gonna click a few times. So it's the logical zero is just the antisymmetric Bell state defined using frequency bin qubits, and the logical one state is the antisymmetric time bin state, antisymmetric Bell state using time bin qubits. So we're just basically saying that if we had the single photon frequency bin and time bin qubits, then it's basically our 0, 1, minus 1, 0, but defined with the frequency bin states that we defined, and the time bin would be 0, 1, minus 1, 1, 0, but with time bins. And then if we wanted to produce superpositions of these for the plus and minus states, it would be that. Does that answer the question?
Yeah, I think so. So I guess that's when you went to the Q quartz, and then you then want superposition of these two.
Oh, you're asking about the 2 Q quartz thing. Okay, sorry. If we went to the 2 Q quartz state, then yeah, basically we can rewrite our 0t, 1t into we can rewrite our orthonormal 2 Q quartz state in terms of these states, and so then we could rewrite these states into a 2 Q quartz basis. I can show you the technical maths of it later if you want.
Yeah. All right. Thank you. Yeah, that's answered my question.
Okay.
Yeah, thank you very much for the talk. I was wondering, when you compared, I think it was on slide 40, for example, BB84 protocol to yours. You said that there would be a couple of, or many detections being needed in order to estimate the error in the channel.
Sorry, so here?
Or actually to compensate the errors introduced by the channel. And I was wondering what you exactly mean by this. Because, for example, for our system, with the time and phase encoding, we do not need to compensate anything, even if there's a phase
if you use
polarization drift, for example. In the
so you're saying if I use, say, time bin encoding, for example? Instead?
For example, exactly.
Yeah, so this one, I believe, was a polarization compensation scheme that we showed here. But if you use time bin encoding, then the compensation, as you go to larger distances, things like chromatic dispersion in the fiber will lead to an increased QBA. And after about 50 kilometers of fiber, this would lead to two large QBAs, and you have to compensate this using dispersion compensating fiber, which introduces extra losses into your channel.
Well, so we're, for example, using our system over more than 100 kilometers of fiber. Of course, it depends on the encoding rate that you're using. What did you assume for this here?
Sorry, pardon?
So at which transmission rate did you assume the systems are working?
So which transmission rate? So here we've plotted it in terms of bits per pulse. Are you asking if we plotted it in bits per second instead?
Yeah, but if you're talking about chromatic dispersion, then your transmission rate actually matters because for higher transmission rates, you're using shorter pulses. So when they have a broader spectrum and they disperse more. So just as an example, I wanted to say that, yeah, this maybe could be interesting to take into account in this comparison.
I'm sorry, I couldn't quite hear the last bit of what you said.
Okay, so I guess it would be interesting to also take into the account in the comparison the transmission rate, because it has a direct influence on how bad the dispersion is actually for the transmission.
I see, like if the dispersion is higher, then you could have sort of fewer pulses sent per second.
Yeah, or yeah, like if you have a high transmission rate, the impact of the chromatic dispersion is worse.
Yes.
Yeah. And you can, just as a side note, also pre-compensate the chromatic dispersion with a DCF fiber inside Alice and accordingly increase the transmission, or such that the mean photon rate, mean photon number leaving Alice is actually the one you want, and then you do not introduce additional losses.
Yeah, I see your point. I think the kind of point to highlight from our scheme is that there are obviously multiple different ways to encode the information, and there might be in particular channels different ways which have more advantages, but we can avoid some of these challenges with our scheme. Yeah.
Thank you.
Thanks.
Hi, thank you for your talk. Please, in slide 38.
38.
You mentioned that the curve oscillates there.
Yeah.
It means no key rate. But I was wondering, when the theta is randomly, each point in the curves has a positive key rate. Why you mentioned is no key rate?
Yeah, of course, sorry. I maybe didn't make that completely clear. Essentially, what this, sorry, where's my, okay. Basically, this central peak here, you can actually consider more like a sort of a negative curve, which in a post-processing step, it's basically saying, here we've assumed we have a fixed angle theta and try to find what key rate we can get. And if we have a fixed angle theta, then this would actually be completely anti-correlated. So it'd be like a negative curve, and it gets flipped in post-processing.
Okay, I get it.
Yeah.
Thank you.
There's a question there.
Sorry, can you go to the next slide, please?
Yeah.
So, yeah, can you tell me how you calculate the key rate at the zero losses? Because I'm one of the author of this paper. 10 to minus 3 at zero losses seems a little bit low.
So what we did for this one is we calculated we took the key rate reported at the certain loss reported. So I can't remember exactly how many dB it was, and then by using a conversion. So was it if it was twin field QKD, it would have been square root transmission at 0, which is 1 over transmission at.
So because I think what we reported was a very high losses when you have let's say the knees of the key rate. So it's not in the, let's say, in the linear range.
Yeah, exactly. We kind of assumed it's linear. Of course, it's not.
So the data that probably you took was not in the linear range. So because these numbers should be much higher in the real experiment.
Oh, it was
these
on
numbers,
the curve bit.
Yeah.
Okay, I see.
So just
Sorry, thank you for informing me.